This is the Unit 4 review for your Unit 4 test. We'll start with question number 1. We have several graphs here. We're asking which graphs represent the residuals. This is going to be an important thing that we go to. The residuals, not the points that are from our table, but the residuals from that graph for a scatter plot that is fit well by a linear model. Now we know that a scatter plot is fit well if our R, the number that we get in Desmos, is very close to +1 or -1. All right, so one of the things I'm going to eliminate first off the bat is graph number 2, because this looks like a curve. So I'm going to take that out. I'm going to also eliminate number 4, but not necessarily, because it looks very loose, but it's not, and I said not necessarily because there's a line right there. If that were the x-axis, I would consider this, but this is not the x-axis. The x-axis is down here, so that's out. I'm going to eliminate 6 because it kind of scatters out and opens up. I don't want that either. Okay, I'm not going to choose 1 because all those dots are below. They're below. This is the x-axis, but they need to be kind of on both sides. So I'm going to eliminate this one, and I'm going to eliminate 3 because we don't have them split out kind of above and below. And I'm going to eliminate 7 because this is a different type of graph. This is the graph that we've been used to looking at. It's going to be number 5, and I'm going to show you why. If we're graphing the points from our table, it's going to look something like this, or some of these other graphs perhaps, not number 2, not a curve. But residuals, I'll show you how to do that in Desmos. All right, I'm going to use the data from question number 6 just so we'll have it ready to demonstrate how plotting or graphing the residuals is a little bit different than graphing the points from your table. So start out by adding an item, click on the plus, and we're going to go down to table. Check to see that you've got x sub 1, y sub 1. Okay, I do. So I'm going to put 50, 75 for my x values, 100, 150, and 200. Oops. Double check. That doesn't look correct. 50, 75, 100, 150, and 200. Now let's put in our y values. 18, 15, 12, 7, and 1. Underneath that, I'm going to write my equation for the regression line. In other words, the line of best fit. We're going to model it after slope-intercept form. So we'll start with y, and I'm going to put sub 1. Just write the 1. It will drop down by itself, equals mx, put the sub 1, plus b. Now if you notice, my y's disappeared. One thing that I forgot to use a tilde instead of equal. So I'm going to hit shift and find that squiggly, that tilde key. Alright, so now this looks correct, and it gives me data down here that's going to be important. But I'm looking for these points that are plotted, and if you notice, my x's go from 50 to 200, and my y's go from 1 as the smallest to 18. So let me make some adjustments in my graph. I'm going to click this wrench. On the y-axis, I'm going to start here first. I can start at 0 because I don't go below 1, but I do want to see where it crosses the x-axis. So let me go ahead and go from 0 to my highest number is 18. So I'll just go up a little bit to 20. And then on the x-axis, we're going from 50 to 200. So I will change that from, I can go from 50 to 200, but I'm going to go from 0 to 200, and I'll show you why in just a minute. All right, so that will zoom in a little bit. You can also change how we're counting if you don't want it to count on the x-axis in the increments that it is. But I'm going to do that, and I can zoom out a little bit. I can see where it crosses the y-axis. Where x is 0, y is 23,448. So there's a lot I can see. And I can see where those points are by clicking on them. They're not exactly on the line, but they're close to the line. So I'm going to look down here to r. So r is a number between -1 and +1. So you can see this is negative 0.9994. So it's going to be a negative slope, and it is, those dots are going to be not perfect. If they were perfectly on that line, this would be -1, but they're going to be very close because this number is very close to 1. So that looks correct. But this is not the graph that we want to look at. We want to plot the residuals. We get that by clicking on this E sub 1. So let me go ahead and click that. Now I see little dots show up at the bottom, and this is showing me how far away those numbers are from that regression line. Okay, so they're not very far off. Okay, they're very close. So what we're looking at in our graph is we're looking at numbers that are around 0 on the x-axis. Above, a little bit above, a little bit below. The closer they are to that x-axis, the better fit that we have. All right, so coming back to this, we see that number 5 is the only one that's going to be a graph of the residuals. So look carefully at the question and what it's asking. It will help you to answer correctly and more quickly. Question number 2 is about hiking. The graph relates temperature. Temperature is going to be our y. And altitude. Altitude is going to be our, what we have on our x-axis. And if I look, I'm moving up by 2s. I'm counting by 2s on the x-axis. On the y-axis, I'm going up by 10s. 0, 10, 20, 30, and so forth. All right, so I see my y-intercept. My y-intercept is 60. And the slope is already calculated for me, negative 3.6. So the slope is telling me it should be a negative slope, so it is slanting down. And for each increment of 1, not of 2, it's going down 3.6 degrees. All right, so I should be able to tell you what's here, by going down 3.6 for every unit. But we're counting by 2, so we double that. All right, let's look and see if we can answer the questions for number 2. True or false? The temperature is lower at 6,000 feet than at 4,000 feet. All right, so we can already tell that it's going down. So as we move from 6,000, we are at, no, that's not 6,000, that's 60 degrees Fahrenheit. So let's go 2, 4, 6, and this is in thousands of feet. So at 6,000, I'm here. If I look at my regression line, and at 4,000, I'm going to be higher. So the temperature is lower at 6,000 than at 4,000. That's going to be true. As the altitude increases, the temperature decreases. So go back and make sure you're looking at altitude. So as altitude increases, let's just pick a place up here. go from 4,000 to 6,000. Is the temperature going down? Yes, the temperature is decreasing. So that's going to be true. C, true or false? The value of the correlation coefficient is very close to -1. So let's look at the correlation coefficient. That's going to be R. R is -0.89. So that's close to, if this were -0.5, it would be really hard to tell. There would be a loose correlation. If it were 0, there'd be no correlation. But this is close to 0.9. 0.9 is closer to -1. So it's going to be a strong negative correlation. This says there's no association. It's already telling you that the correlation coefficient is close to -1. So that should be a correlation. So this is going to be false. All right, the line of best fit for part D indicates that in general the temperature 6,000 feet should be 3.6 degrees lower than the temperature at 5,000 feet. So at 6,000 feet, let's look and see how far we've moved. We've moved a unit from 5,000 to 6,000, 5 to 6. All right, so that should be one of these, -3.6. So that is true. 3.6 degrees lower. That negative says we're going down. All right, E, the y-intercept from the line of best fit indicates that if the linear trend holds, the temperature should be 60 for 0 degrees altitude. So let's go at zeros on the altitude x-axis and go up here. And yes, we already said that. That's 60. You can see that from the graph, or you can see it from the equation. That's going to be your y-intercept. So that's going to be true. Question number 3. 21 young men got a quote for the cost of a car insurance policy. The policy cost and ages of the men are shown in the scatter plot. So let's look at the scatter plot. We have a line of best fit, or a regression line, and we've got points above and below. Okay, so let's look at this graph. What do we know? We want to select all the statements that are true based on the scatter plot. We don't have a table, we just have a plot. So on the bottom, on the x-axis, we're looking at age in years. And we don't start at 0. We start here. We don't see the whole thing. We just see a part. But if you look at how we're counting, we're going up by 1. 18, 19, 20, 21, 22, 23, 24, and 25. All right, so the x-axis is showing age in years. And the y-axis is the policy cost in dollars. All right, so let's just check. Every 20-year-old pays a lower amount than every 19-year-old. Now, when it says every, this is where they're going to try to trick you, that every, this word every is a qualifier that we want to really slow down and not just check one thing. We want to check every point. So we're looking at every 19 and 20-year-old. Does every 20-year-old pay a lower amount than every 19-year-old? So let's go up. Here are the 20-year-olds. And here are the 19-year-olds. All right, this 20-year-old right here is paying a lower amount than all three of these. This 20-year-old is paying a lower amount than all three of these because that dot is below all three. But this 20-year-old is paying a higher amount than this 19-year-old. So that's not every 20-year-old. So that's going to be false. All right, the cost of car insurance increases as the age of the driver increases. Did I say that correct? Let me read it again. The cost of car insurance increases, so car insurance is going to go up as the age of the driver increases. So let's just take the 19 and 20-year-olds. So car insurance, let's look at the regression line. For 19-year-olds, it's going to be around $3,000, and 20-year-olds is going to be around, it's going to be less than that. So as we go up in age, is the car insurance increasing or is it decreasing? Read those carefully. It's going to be false. Car insurance decreases as the age of the driver goes up. You see it's going down. There is no correlation between insurance cost and driver age. That's false. There is a correlation. We can see it. Okay, there's a strong correlation, and we can see the R factor up here. It's negative 0.951, so that's very close to a -1, so that's a strong negative correlation. Okay, no correlation, R would be 0. And let's go ahead and move to part D. There's a strong negative correlation between driver age and insurance cost. Okay, we're just repeating what we said. Strong negative correlation. Negative correlation is going to go down. The line of best fit indicates that a 20-year-old driver pays about $300 more than the average 21-year-old driver. So let's look at the 20. Let me erase this. Let's get this out of the way. All right, so we're going to look at a 20-year-old driver. It's going to be up here. It's going to go across, just approximate, and 21-year-old driver. Now we're going to look at this two different ways, so I don't want you to get confused. It's really hard to read from the graph, but we know we're only going up 1 year, 20 to 21. So that's an increment of 1. So for every increment of 1, that's going to be our slope. It's going to go down $315.67. That is about $300. It's going to go down from 20 years old to 21. So does a 20-year-old driver pay $300 more? Got to think about what that's saying. And that answer is true. Question number 4. Mr. Thomas wanted to know if the amount of class time that he gave students to study affected their test scores. The scatter plot below shows the results. The data in the graphs suggest a linear relationship because you can see that you could lay down a line of best fit. So let's look at what that line of best fit looks like. I'm just going to draw, I'm trying to decide what to draw with. I'm just going to draw with my highlighter. Okay. It'd be something like this with dots above and below. All right, now let's look at what direction that's going in. It's going to be positive, so I'm looking for a positive slope. We have a negative slope here, so I can go ahead and eliminate this. This is not an equation of a line with a positive slope. Okay, we also have a negative slope here, so I can eliminate D, A and D. So we have 2 to choose from. Now let's look at the y-intercept. So we have 90 and we have 64. So looking at that regression line, that line of best fit, what goes along those dots, if we lay it down, which one of those numbers is less than 70? That's going to be 64. 90 is too big. So we're going to eliminate B, and the answer choice is C. This is not hard if you understand how to read that graph and what it is that we're doing. Question number 5. Kiki collects data about the number of leaves on school property and the average games won for those schools. Kiki says the scatter plot shows a strong positive correlation. Now, you're going to hear words like correlation and causation. Okay, leaves on school property do not cause games to be won. I don't think that that's a causation, but there is a correlation. So there's other data that goes with this that we don't see. But there is a correlation. And that correlation shows an increase in the number of leaves and team wins. What does it mean for the relationship when the correlation is strong? A strong correlation means the data lies close to the line of best fit. Another way to say that is the number of leaves and games won are close to the line. So there is a correlation. What does it mean for the relationship when the correlation is positive? It means that a positive correlation says that both variables are increasing, or more leaves usually go along with more wins, or when the leaves go up, we have more leaves, the games won increases. But what is wrong with that sentence? Again, although the variables are related, one does not cause the other to happen. Question number 6. Now this is what we put into Desmos for the data. Water depth, we've got a table. Water depth in meters is going to be X, and temperature in Celsius is Y. And we graphed the residuals. Let me see if I can open up Desmos or go back to that and show you. If we click on the E sub 1, it'll give us all of the residuals for this set of data. Give the line of best fit. Again, put your table in and you'll have the slope and the intercept, and I'm rounding off to the nearest hundredth. I'm going to write y equals negative 11x plus 23.45. The test will probably tell you, but if it doesn't, go out to the nearest hundredth. Give the residuals for each point. So this point is 5018. The residual for that point, how far it is away from that actual line, that regression line, is 0.5 or 5 hundredths. Okay. The residual for this next point, 7515, is negative 0.2. The next point, the residual is negative 0.45. The fourth point, 157, the residual, and you're getting all this from Desmos, is 0.05. And then finally, the point 201, the residual is negative 0.95. Is the line a reasonably good fit? You can look at your R, and yes, the points are close to the line. You can look at the graph. Explain the meaning of the slope. As the depth goes up, the temperature goes down. The slope is a negative 0.11 or 11 hundredths. Describe the relationship using the correlation coefficient. It is a strong negative correlation. Again, it's very close to negative 1, so it's a strong negative. All right, let's look at the data for this table that we just did, and let me explain that again. You're going to click on E sub 1 and plot it, and you're going to get some dots down close to the x-axis that plot the residuals. And it's going to show, if it's close to that x-axis, it's going to be a Very close correlation. This is a negative correlation. Here's your slope, and we round it to the nearest hundredth. And here's your intercept. We round it to the nearest hundredth. And the slope is going to round to 23.45. So this is the data that you should see when you try it yourself in Desmos. We did this earlier. Now, one thing to mention, this table can come up with x sub 2, y sub 2. So always check to make sure your table says x sub 1 and y sub 1 so that you get the correct graph in the line of best fit. Click on E sub 1 to graph your residuals. Okay, here's your slope and here's your intercept. Question number 7, we have a table. We're going to put that table into Desmos. I'm not going to do it for you. I'll let you practice it. Okay, our x is going to be diameter in inches, and our y is going to be age in years. So if you get your information from Desmos, the regression line, and you're rounding to the nearest hundredth, the slope is 6.45, and it's a positive slope. Put that with x minus 15 hundredths. B, describe the relationship of any outliers. Outliers are going to be points that do not, they go far away from that regression line, and I didn't see any outliers there. Okay, the correlation coefficient is 0.95. It's a strong positive. And the slope is going to be a positive slope. So what that means is for each year, the tree diameter increases by 6 and 45 hundredths inches. Interpret the y-intercept, and does it make sense? So the y-intercept is negative 15 hundredths. All right, so the starting diameter, since we're talking about the diameter, the starting diameter can't be negative, so that does not make sense. We want to calculate the residual for a tree with a diameter of 9 inches. So when we graph that, you can look at 9, or you can actually put the 9 in here. Slope times x, 9, minus 0.15 is 57.9. You can get that actual amount. Okay. The actual is 49. That's what we got from our table. And the predicted from our regression line would be 57.9. Okay. If we take that difference, we subtract the actual from the predicted, we get negative 8.9. That is how we get our residuals. Okay, again, just looking at this data, diameter and age in years, this is what your graph should look like. This is our regression, or our correlation coefficient. It's a very strong positive, so those dots are going to be close to that line. And then our slope is 6.45 rounded. Our intercept is negative 0.15 rounded to the nearest hundredth. So y equals mx plus b. This is the equation that you need to have written down in your notes to put into Desmos to get that regression line. Question number 8, we have a table again. This is a table of a convenience store manager, and he notices that the sales of soft drinks are higher on hotter days. So here's a table of temperatures. As the temperature goes up, the number of cans sold goes up. So we want to write the equation. Again, we're going to go to Desmos, and we're going to put that information in. And then we're going to write y sub 1 tilde mx sub 1 plus b. And we'll get a graph that looks like this. So you can practice that to see if you can get that adjusted so you can see it. But you'll have this data here. So this is our correlation coefficient. It's going to be a strong positive. If you want to see the residuals, you can plot it, but we don't need the residuals to answer this question. Here's our slope, 16.42. If we round it, and our intercept, negative 621.83 if we round it. Okay, so let's go back and use that to answer these questions. The equation, y equals 16.42x, that was our slope, minus 621.83, that's our intercept. Okay, the correlation coefficient, again, here it is right here, 0.9673. That's a strong positive. So we found it. We're going to interpret what that means. 9.67 is strong positive. Interpret the slope. Let's go back and look at the slope. The slope is negative. So what that means in context of temperature and number of cans sold is that as the temperature goes up, sales go up. Temperature goes up, sales go up. Slope is positive. It goes up by each degree, 16.42 more cans are sold. Use the model to predict soft drink sales if the temperature is 95 degrees. Okay, so let's see how to do that. We're going to take our equation. We're going to substitute in 95 for x. If you have this graph, you can also use the graph to answer, but I'm going to use the equation. So we're going to put 95 in for x. X is always the input. Minus 621.83, and you get 938.07, or approximately 938 cans. Okay, here's the data, the table, the graph. And don't forget how to plot that regression line or line of best fit. Question number 9. Correlation means that two events are related. Association is another word for correlation. Causation means that one event causes the other, kind of like cause and effect. Okay, we have the number of miles driven and the amount of gas used on a trip to Disney World. Is this causation or correlation, or both? Okay, the more miles that we drive, of course we use more gas, unless we're using an electric car. The amount of cars a salesman says and the amount of commission he makes. Again, the more cars that are sold, the more commission. If a salesperson is working on commission, okay, that's going to be a correlation. So I'm going to put CO for correlation, and I'm also going to put causation. CAU, causation. Okay, so this one has causation and correlation, it has both. You hit your little sister and she cries. Now that's a causation. Okay, normally if you hit somebody, especially younger, a little kid, they're going to cry. So what you did causes this to happen. Is there a correlation or a relationship between the number of times she cries? Yes, that's going to be both. The number of cars traveling during a holiday weekend and the number of accidents reported. That's both correlation and causation. But actually, no. You could argue there's no causation. Number of cars traveling, does that cause more accidents? I'm going to say, looking deep at the data, yes. More cars cause more accidents. So that's again both. The number of cold, snowy days and the amount of hot chocolate sold. Now there is a correlation. Is there a causation? Does the cold cause more people to want hot chocolate? And I would say yes, that's going to be both. The increase of warm, sunny days and the number of ice cream trucks visible. Again, causation and correlation. Correlation first, causation yes. The number of pets someone has and the number of books a person's read. Okay, there's a correlation, but having pets doesn't cause someone to read books, so there's no causation. A person's height and how fast they drive. I'm not sure if there's even a correlation, but there's definitely not a causation that I'm aware of. Test scores and shoe size. No correlation and no causation. All right, hints on rounding. Look at the number behind the digit, following the digit that you're rounding to. If the number is 5 or greater, you go up. So let's look at some examples. Round to the nearest hundredth. Okay, so this is the decimal point. This is the tenths place, the hundredths place. So I'm going to look at the digit after. 6 is greater than 5, so I'm going to add 1 to the 4. So that's going to be 1.85. Okay, nearest hundredth again, so I'm going to go out to the 3. 7 is greater than 5, so I'm going to add 1. It's going to be negative 26.04. Going to go out to the nearest hundredth. Look at the next digit, that's a 3. 3 is not greater than 5, so that's going to remain 375.92. All right, now we're going to round to the nearest whole number. The whole numbers are on the left-hand side of the decimal. So I'm going to look at the digit directly following the 8. The 3 is not 5 or greater, so that's just going to be negative 8, making that a whole number. Round 7 to the nearest whole number. So I'm going to go to the right and look at the 6. 6 is greater than 5, so I'm going to add 1 to the 7 and make that positive 8. Again, we're rounding to the nearest whole number. 6 is greater than 5, so I'm going to add 1, negative 1 to negative 5 and get negative 6. So I'm just going to bring that up. So just practice in rounding, so when you're asked to round, you'll know how to do that. All right, something I want to mention here that we may not have talked about, not even in the book, but let's talk about it now, so if you see it on the test. The table below gives the amount of time students in class studied for a test and their test scores. Graph the data on a scatter plot, find the line of best fit, and write the equation for the line that you draw. Again, we modeled this. I'm going to put this into Desmos. And then you're going to see that little E sub 1. You're going to hit that. This is going to be your X. This is going to be your Y's. Okay, when you hit this button right here, it's going to give you a separate column of residuals for each of those two numbers, and you're going to put that here. The linear regression equation you get by finding the slope and intercept. So we're going to start with Y sub 1 tilde m x sub 1 plus b. Okay, the correlation coefficient is going to be the r, and you're going to put that in right here. And the type of correlation, if it's positive and it's it's close to 1, like 0.9, it's going to be a strong positive. If it's less than 0.5, it's going to be a weak positive. If it's 0, there's no correlation. And then using your linear regression equation, you can predict a student's test score if they studied for 4 hours. So you can go on that line, or you can plug it back into the equation that you get, y equals mx plus b. This is an interpolation extrapolation. So these are two words that you'll see on the test that are not in the book. Interpolation, extrapolation, because we are interpreting what that's going to be with the regression line, which predicts but doesn't always accurately give us the score. We use the linear regression equation to predict a student's test scores if they studied for 2 hours. All right, again, interpolation, extrapolation means that we don't have the exact numbers, but we're using data to get a pretty good idea. We click the plot button, that's the E sub 1, to determine the residuals, and we round those to the nearest whole numbers. So some tips for test taking. Okay, again, interpolation, extrapolation just means we're giving our best guess with the data based on how those points are plotted.